All right, so we're back to another panel. One of the topics that was raised several times on the program committee and actually in some of the surveys from last time were to talk a little bit more about what's going on oh, nice to see you can make it. Monitoring and measurement, and it's a hot topic for so many different reasons. So what I'm here to do today is sort of just facilitate, because we have a panel of people who know this inside and out from both the operational and the research community. So I really want to get to letting them talk, but I just want to give a few minutes of an introduction. So I'm going to do that. Oh, by the way, this is another picture Lucy helped me with on the theme of this NANOG, and I'll explain it in a second. I don't think I used this one, but remember that picture. So here's what I'll just do: a little bit of an introduction, panelists and their presentation, and we'll do a discussion and some question and answer. And I've kind of modified my strategy here after yesterday. So to just be in keeping with the spirit of the NANOG in Eugene, or in Eugene in general, here's a monitoring problem. It's really at scale. This is another picture of the thing that was on the front of my slides. This thing was called the Wall of Sound. How many people know what that was? This was built by JBL for the dead back in the late 60s. And if you look at this thing, you realize that they had a pretty interesting monitoring problem. They had a lot of wattage, and about 40% of the Wall of Sound had to do with stage monitoring. The other thing that Greg Shepard pointed out just about 5 minutes ago was that monitoring like this, and it's kind of a nice metaphor, monitoring takes a lot of infrastructure. So if you look at what these guys had to do to get that stage monitoring up there, you notice that infrastructure is important to get it done. So that's one kind of monitoring.
Dave?
Yeah?
One of the speakers was wired backwards.
Oh, yeah. I think it double counted the amperage too or something. Back in our domain, or maybe that was our domain, but anyway, this one, there's a lot of things we're looking for measurement and monitoring systems in ISP backbones to help us with. I'm going to list a few of these, and then I want to just get off and let these people talk. So let's see if this can work. Traffic engineering has been a big one. It's kind of been beaten to death. We'll see a little of that today. Performance and SLA verification, of course, that's important. This is a big one: DOS detection and mitigation. Forecasting and capacity planning, that's huge. Sampling versus accounting. There's requirement issues for hardware and software that need to be addressed. There's a lot of studies going on about convergence, IGP and EGP convergence, and that, of course, takes a monitoring and infrastructure to do. And then there's also the wish list. Why can't we do this in our routers, or can we do this in our routers? What are the problems there? So these are a few topics that come up frequently. What I did was I asked each of the panelists what they would like to talk about or what they think is interesting, and so here's what we came up with. Oh, okay. First off, I modified this a little bit. Yesterday what I tried to do was I tried to get the panelists to discuss each other's presentation so that we'd have like panel discussion, it being a panel and all, and that more or less cratered. So my plan today is just to let them have 10 minutes to go, and then we'll take the rest of the time, the 13 minutes or whatever they have, for question and answer, and we'll stretch it out through the end. So here's what we got. This is me. Tony's going to talk about the role of measurement and capacity planning, SLA maintenance and verification. Christoph's going to talk about what kind of monitoring is, what are the operational aspects of this. Mujahed's going to talk about DOS mitigation in the backbone, the issues and the mitigation strategies that they use. Jen's going to talk about what's needed from the vendors and an IETF PSAMP update. And then Chris will talk about traffic analysis in their backbone. And that's all I really want to say. I want to let these guys get going. So, Tony?
All right. My topic, or my presentation, I should say, is kind of more generic overview of the topic, and some of the things were actually touched on a little yesterday in Thomas's talk and in the availability talk that, and then the availability talk that the guy from Juniper gave, gentleman from Juniper. So, a couple of different approaches that meet in the middle. The analytical, take from the one side the analytical using models, numbers from vendors and industry literature like MBTF, fiber cuts, probability of fiber cuts over distance, simplifying assumptions mixed in there like reducing the number of nodes in your model to improve computational feasibility, some rules of thumb. On the other hand, you've got the empirical, that's the observation-based, instead of the theory, more of the observation, things that you measure in the real world like interface counters, flow stats. For capacity planning, the basic inputs and method go something like this, or so the people who do that stuff my company told me. You derive a traffic matrix, take in topology, IGP costs, run SPF offline to figure out what routing would really be like, on the network at any given time. Gather flow stats, reconcile those with interface stats, assume rough conservation of flows. Traffic in equals a traffic out. Never exactly, apparently, but that's an assumption. Model that onto the network, trying to find the best fit matrix for all the information you have. To say that the flows match the interface stats you find along the way, given the routing that you've derived with your offline SPF analysis. Then try what-if scenarios, including failure analysis, generally single failures with shared risk, relationships. If this box fails, then this card fails, then these links fail, or if this fiber cut happens, then these bunch of links go offline. Multiple unrelated failures add another dimension to the matrix, but probably not that important to model all those different combinations given the lower likelihood of happening. Then there's a lot of other stuff you have to pepper in there, looking at the empirical trends, incorporate the sales forecasts, who knows where those come from. Then there's, the fact that the demands of a given sale, a customer wants to hook up an OC3, but it's not a point-to-point like in a ATM or frame network that you can model on. Because you know where it's going to go. They don't know where their traffic's going to go. Is it going to go to a local peering point? Is it going to come in from a local peering point? Is it going to be on-net, off-net? Consider the exogenous factors, things that you know about in your head, but are hard to model in. Changes in exit capacity upcoming, with new interconnection points coming up or down. Behavior of large sources and sinks. Very big customers may shift their traffic. Some of you may know about this. Among providers, the law of large numbers doesn't apply because if you've got a OC48 uplink to a router and then all of a sudden the OC12 customer lands on it, that kind of blows your projection pretty well. Construction delays are another thing. We don't know what intervals to expect. So the average build out for a certain thing may take 3 months, but sometimes something balances it up and drags out to 12 months. How can you model that into your expectations? And what are the economic ramifications? Lost sales, customers leaving, who knows, versus the, relatively easy to understand thing. If you've got something 3 months too early, you can, you have to operate it and depreciate it over those extra 3 months. But it's probably less risk, and I think Dave referred to that in his presentation yesterday. And then there's things like new applications, which can totally blow your assumptions too. Peer-to-peer file sharing, data replication, very different types of traffic profiles. Things that you have to contend with that can make things tough. Sampling, so you're basically grabbing a counter at different time intervals. You're inferring the rate by dividing the difference over the time, but the detailed information about what happens on actual traffic arrival rates in that interval isn't present in that sample. There are bursts where instantaneous offered load exceeds instantaneous capacity, leads to a little bit of queuing, a little bit of jitter, maybe a little bit of drops, but those can happen on potentially on very short scales that we don't know about. then internet traffic is very variable and appears to be somewhat self-similar. I guess, actually, based on dinner conversation last night, there's other ways to characterize it. Maybe some of the other speakers will touch on that. But the upshot is when it's aggregated, the peaks don't smooth out so much, and fat pipes need commensurately big overhead to handle the big bursts. And then there's lots of time of day, week, and year effects to contend with. The latent demand is hard to determine given the mix of elastic and inelastic traffic. Removing one bottleneck may just reveal another one that you didn't know about. A few more challenges. How well does the approach scale? We got to grab all these stats from so many devices. Where will that take us? And given that, we have to figure out what are the most important things to grab because we can't really get it all. And then you've got vendor problems, mid counters which are not compliant, missing or broken. Same with flow stats. May be working one day and broken the next by some new hardware or software. All kinds of headaches there, logistical headaches. Then you also have to consider that the back-end systems which drive this, the databases and offline tools, have to gather the same. Besides gathering the raw stats, they have to gather the hints about the topology and routing, so that at any point when you want to look at historical data, you have to map it to the appropriate topology to make useful sense of it. On to the SLA topic. So it's really about marketing. So some people offer 100% availability. Is that real or is it marketing? SLAs sort of involve these four things that converge in a sort of unusual way. Basically it's in one way, what would you guarantee to the customer? What is the customer expecting based on what you've said, what the network is designed to achieve, and how the network actually performs? And out of this you produce a number. Does it reflect all those things, and does it make everyone happy? That's something to think about. It's hard to compare different companies' SLAs because they're far from being apples to apples. People measure things in different ways, and when you get down to it, it's really about balancing the risks. So if you is an SLA what people really need to figure their traffic that definitely will always be delivered, but if it's mission critical, they usually have a backup system of some sort. I mean, they're not really, they may get the money back from you, but that's not money that they're really interested in if their business is severely compromised. So would you trust your life to IT? Well, maybe if you could set the toss bits, but I don't know about that. So you can give all the guarantees in the world, and it might not go for much. Some metrics that people care about: availability, latency, jitter, and packet loss. These are typically the things that are cited in SLA agreements. But whether or not the applications really care about them and misperform is something that people don't often understand about their own applications. So they may look for the number, but does it really get them to the end goal that they want is an open question. Do our measurements catch extremely transient events? Because that's where the bursts and loss happen. Well, there's obviously a loss that happens as a result of failures. Those are important. But there's some other things that we don't think we can measure. We did one internal study to see what kind of sample period we wanted to use, and introducing episodes of loss with two probes that have the same period or out of phase. One or the other might catch the episode, and as the time was cranked down, and as the period got close to about 1 second, both would generally reflect the loss. So the duration of the burst was, had that kind of resolution, and that gave us a sense of, how often to measure the performance of the network, how many probes to send. Some functional challenges. what we can actually measure is it basically serves as a proxy measurement for what might be most of interest to a particular user. So, customers want a measure of the delay of the network, but is it really the delay they experience with their application from their particular location to some other endpoint? Not exactly, because that's point-to-point SLAs would involve sending test traffic on the exact same data path as any particular customer, and given the number of sort of point-to-point unicast streams, it's just not feasible, and you'd need more test equipment, kind of like what Dave was saying. The monitoring equipment you'd need to deploy, the monitoring infrastructure would start to become incredibly cumbersome and expensive. Then there's the challenge of correlating measured data with known events, planned maintenance, customer-caused outages. When certain blips in the measurement data, have to be scrubbed so that we can see, all right, well, that was was this part of something that was planned maintenance or wasn't it? That's based on, did the routing traverse this particular node that we took out for reload or something like that. And then as time recedes, as we need to go back and correlate what happened because people ask for refunds or whatever, to figure out whether it's really part of, was really part of a maintenance window or whatever. As that recedes in time, it's definitely hard to reconstruct. So big picture, education, because the numbers can be pretty confusing, and trying to interpret what they're actually telling us definitely can be a challenge, and have to kind of help sales staff set expectations, help support staff explain numbers that come out in reports. So all of that is pretty involved, and it's hard, it's not impossible to design the system to a quantitative behavior given the changing demands of the whole network. So that's something maybe we'll get to in the future, but and maybe there'll be fodder for discussion if we have some more questions. Then, of course, the business questions are definitely TBD. How much will people pay for premium performance or the promise thereof? And how much is this buying for either us or our customers? No one really seems to know that. They waive the term table stakes, and that's just where it sits. So, but of course, you have to spend money to achieve certain things. So there's no kind of reconciliation there. Just acknowledgement and thanks to the folks internally who helped me with this, and that's it.
I want to hold questions this time because I think we might have started late, but according to my time thing, I'm way behind. So after Christoph, we'll take questions then. If there are any.
Okay, so the goal of this talk is really to try to answer the question: how can we keep using the kind of monitoring infrastructure we have today at ISPs, or how can we evolve this infrastructure to something that could be used for management and design and operation purpose? So let's say that 4 years ago we started at Sprint Labs in California. We started with a mentoring project, and at this time the motivation was mostly research. We had the feeling that we could help people in engineering and service and operations to do a better job, to improve, to do it easier, to manage a better network, but we didn't know exactly what. So we had to start with a very brute force approach to monitoring. And what we decided to do is to bring the POPs and put box that could tap the fiber and put box that could connect any IP packet and timestamp the packets, so that we have the maximum possible information on the traffic to study and to see how we could help. That's what it is today. We have 4 POPs where we have monitoring equipment on OC48 links, OC3, OC12, a little bit everything, and we try to understand how the traffic is behaving. One of the problems is we have to bring all the data back to the lab. It's huge. I think it's something like 1 terabyte for each POP for 24 hours minimum. So that doesn't really scale. But after 4 years, what I think we can claim that we have been able to help engineering and operations at Sprint with the network. Ted would tell you that we have been creating a lot of trouble too, but that's one of the drawback. But I think that it's positive after 4 years, and we have been able to help on all the issues that's on this slide. And I will not repeat them because I think it has been in a previous talk and it will come in the following talks too. But we have been able to study things like link failure, to design forecasting tools, and I give you a website at the end where all this data is available. So now the problem is, if we want to migrate such a monitoring infrastructure to operation, we need to have all this information available almost at any time. We don't need to have them available systematically, but when there is a problem, when there is an anomaly, when there is an issue, something we want to know in the network, we need all this information. There is no way we can make a decision with a subset of this information. And that's where our monitoring infrastructure fails today. Just the packet is not enough. So we need timestamp IP headers, we need all ISIS and BGP information, and if possible, we need to be part of the BGP mesh. Okay, being a simple BGP speaker is not enough. You don't see everything. We need the lower level alarms, if any. We need the SNMP information, and recently we could realize that SNMP information was pretty bad and not very useful. So maybe we need to improve that, and we need the router logs. And based on that, we think that the approach to monitoring should be a 2-level approach, with first level where you continuously monitor each link and compute a small set of statistics that can deliver you the general health of your network, tell you if your network is going well or is going bad. And for example, you need the volume, you need the peak traffic on very small time scale. You need the number of flows, maybe distribution of packets, the number of out of sequence packets. But this kind of information are needed on a continuous basis. And that's what will be used later to know that something is going wrong in the network, for example. What we need to is store the packet trace for a limited amount of time, because if we realize that something went wrong or we want to know something, we need to be able to go back in these traces. So now the second level of the monitoring system, of the monitoring architecture, is to be able to query your monitoring system at the time you need more information about your network. So the kind of query you could do is, can I know what is the destination POP of all the packets with destination prefix X, or any kind of question related to the dynamic of the traffic or to some statistic of your traffic that you might want to see at some specific time. One of the big issues here is that you need to match the routing information and the packet trace together at any time in your monitoring system. So how to implement this system? Active monitoring is an option, but it doesn't solve all the problems. Active monitoring is good to report data to customers or to get an idea of what's happening in your network, but doesn't give you the high-level granularity information you need to do efficient engineering or operation of your network. The approach we use, which is the OCX-MON approach, is quite expensive. It introduces more equipment in the network, increases point of failure. You have to put optical splitter in all the links. It increases the power requirement and so on. It's not credible at large scale. Okay, so the only location that would be credible is the line cards. And the line card would be optimal, in fact, because that's where you can match the packet trace and the routing information at minimum cost. You have all the information available, the SNMP, the radar log, everything is available in the router. The problem is it cannot. There is no way it can affect the forwarding performance. So the kind of architecture we have in mind is for the line cards, the packet to be duplicated as soon as they enter the line card. I forgot the timestamp. Sorry, I worked on that a lot. Okay, so they need to be timestamped before they go to the memory. But one of the problems is with 1 gigabit of memory, you can store 30 seconds of data at OC192. So it will be very difficult to archive more than that. And what we need is a monitoring engine that can process the data, process the queries, and export the information that are needed by the people that monitor the network. What are the potential problems of this approach? First, at OC192, you have 5 clock cycles between 2 40 bytes packets. We are currently testing the new OC192 cards at the lab. You don't have really time to do much. Even timestamping becomes an issue if you want to do that on a capture card. Even the average size of the packet is 200 bytes, so you can rely on queuing a little bit, but it's pretty dangerous. Query and export might be heavy. If you want to compute delay, there is no way you can compute delay at one point in the network, so you need to do okay. That's INOD security. So query and export might be heavy, and if you want to compute delay, what you can do is the PSAMP approach. You can hash the packet, but you have to export to compute the delay at some point in the network, and we don't know yet how exporting data on the network will impact the network or will impact the complexity of your line cards and of your monitoring system. Potential problem is complexity for line cards, but on this point, a friend of mine working for a vendor told me that if Sprint is ready to give up on multicast and IPv6, there will be plenty of resource in the router that we could use to do monitoring. So maybe this is something we should think about. Memory, okay, as I said earlier, memory is a real issue because last time I talked to Chase Cotton at Sprint, he told me I would like to have 24 hours of archive of data. So that's a pretty significant, it's 2,550 gigs. That's big. Centralized management, so it's related to the exports and query. You will have to have a point, a NOC or something like that, where you can collect all the data, bring all the data, and analyze the problems. To know more, we are trying to put together a website called ipmon.sprintlabs.com. So if everything works, I have some kind of online demo on that. We try to put all the data we collect as well as the reports, the tools we have designed, everything. And it's under construction, so don't expect too much so far. But for example, we have data about the delay and it takes time to download. So you will find this kind of information, delay and jitter on the Sprint backbone between some given links that we monitor. You will find routing information. That's my time? Okay, so you're welcome to go on this website and to send comments and to be convinced that monitoring is very important. Thank you very much.
I still need to make up 5 minutes, so if you have questions, hold on for a second.
AT&T, and I'm going to talk a little bit about what we think router vendors need to be able to provide to help us construct a network-wide view of the traffic and the topology to be able to do a variety of operational tasks. Before I start, though, I want to take one moment to explain the topology of my slides. I've been sitting in the back of the room the past day and a half, so I've tried to adjust my slides to compress the bottom part out. So basically, at a high level, what I want to talk about is that basically there are a bunch of network operations tasks that Christoph alluded to and that Dave already alluded to, and they really benefit a lot from having a domain-wide view, managing the network, not just individual boxes or individual links. So you want to be able to know the current topology, the current offered load, and the current routing information that you get from neighboring domains. And right now, there are a variety of ways to get that information by deploying measurement infrastructure like AT&T and Sprint have done, dumping tables, getting configuration state from the routers, and all these things are quite expensive and complicated, have to be joined together, collected continuously, that type of thing. And then a little bit of lightweight support from router vendors for collecting some of this data would make these things immensely easier. So that's what I'm going to talk about. So some of this is motherhood and apple pie. Other people have already talked about it, and I'm sure other people after me will. There are a lot of basic applications like usage reporting, how much of the traffic is web, how much traffic or individual customer is sending and receiving that one needs. And those to some extent benefit from a network-wide view, but the kind of things I'm really talking about are really basic kind of troubleshooting applications, detecting a problem, knowing that a link is heavily utilized, going beyond that to say what's the reason that link is heavily utilized. Did you have a route flap? Is there a flash crowd? Is there a DDoS attack? What's going on that's actually causing the change in the load on an individual link? And to be able to do that kind of diagnosis, you need more than link utilization statistics. You need some more fine-grained data. You need the ability to drill down to detect and diagnose the problem. And then fixing the problem requires often even more information to be able to do what-if analysis. To say, gee, if I put a packet filter here, what's going to happen if I change this IGP weight or this BGP policy? How's the traffic going to move around? All these kind of activities need a network-wide view of the topology, the traffic, and the routing so that you can actually predict what's going to happen in advance. And particularly for traffic engineering, this is really useful for tweaking routing configuration. And longer-term activities like capacity planning, you want to add a proxy to the network, add a new customer, add a new peer. You want to overlay the existing traffic and the new traffic on the network and see how the network's going to behave after you've made that change. So basically the kind of goal we have here is measurement, not so much for measurement's sake. There's been a lot of work in the research community on collecting measurement data in order to do characterization of the internet. What's the AS graph, how bursty is the traffic, that kind of thing. But here we're really talking about measurement for the sake of control. And in particular, loving the protocols we have rather than necessarily trying to deploy new ones that give us a better view of the network. So the idea is to collect from the operational network a current view of the topology and configuration, the offered traffic, and the routing updates from the edge. Feed those into tools on top that we use for diagnosis, for what-if analysis, et cetera, and then use that to tweak the knobs in the network to better operate the existing network, adding a packet filter, changing a routing policy. Okay, so when I say network-wide view, what do I mean precisely? I mean actually fairly basic things that are actually quite difficult to get. I want to know the topology and the configuration. I want to know what routers and links are currently up, what their capacities are, what routing sessions I have within my network, like IBGP sessions and EBGP sessions to neighboring domains, and the current configuration of the IGP parameters and the BGP policy. So it's the current state. Now, some of that's configuration state that can actually be gleaned directly from configuration data, and it changes on a fairly small time scale. So that's not so hard to get. But actually knowing the operational state of the routers, links, and BGP sessions is a little more tricky. On the traffic side, we'd like to know the offered load between each pair of edge routers or each pair of edge links to know how much traffic is going between different points in the backbone, whether it's at the link level, the router level, the POP level, the AS level, whatever level we're talking about. We want to know how much volume of traffic is going between each pair of points. If we want to play around with BGP, we actually want to know a little bit more than that. We want to know not only the volume between edge points, but how much is going on to a remote destination, particular destination prefix or a particular destination autonomous system. So we might want to know for every entry point in our network, what's the ultimate destination for the traffic that's coming in at that point. So right now people get this today in two ways, right? They do something like NetFlow using the functionality on the existing routers, or they deploy packet monitors like Sprint has done. And this can be quite expensive to deploy dedicated infrastructure, and depending on something like NetFlow is kind of tricky too, because you can't necessarily depend on it being deployable or implemented on every line card that you need that kind of data on. So I'm going to talk a little bit next about lighter weight support for traffic measurement to get that kind of information. On the routing side, we want to know the routes that we get from neighboring domains. What advertisements are we receiving from each of our neighbors, peers, customers, et cetera. And we want to know not just the current best routes that we're using, And we don't want to just dump the BGP cables to get the view from an hour ago or a day ago. We want a current, up-to-date view of all the routes from all the neighbors, so that we know if we make a change in routing policy, what's going to happen. What's the next best route that's hiding that we can't actually see unless we get the full set of routes rather than just the best routes. Okay, so on the traffic side, a group of us are involved in an IETF working group called PSAMP. It's a packet sampling working group. And the goal here really is to develop extremely minimal measurement functionality that can be realistically deployed at high speed. But we want this to be ubiquitous, therefore it really needs to be on the line cards, and also can't be too intrusive on packet forwarding performance because it just won't be implemented on high-speed links, if that's the case. And similarly, we also want it to be tunable in terms of the trade-off between the overhead that's imposed, or the amount of measurement data being collected, and the accuracy of the things we want to use that data to do. Okay, so we want to be able to kind of tune, gee, we want 1 in 1,000 packets of a particular type or 1 in 100 packets. We need to be able to tune that, both to control the volume of measurement data and also to limit the overhead on the routers. So the basic idea is the following. You have packets coming in, you want to apply a filter to them to say, gee, I'm only interested in this particular subset of the traffic. And these have to be lightweight filters similar to ACLs that we already have today. Then we want to do 1 out of n sampling to say, I only want to look at a fraction, 0.1% of those packets to do more meaningful work on them. This could be random coin flip, it could be a deterministic counter, it could be hash-based if you want to do something that's pseudo-random but still deterministic. And then you want to be able to take some portion of those packets and extract that information, IP header fields, local state about which prefix this packet is destined to, maybe what output link the traffic is going to. So some local state derived directly from the packet header as part of packet handling, or the header fields themselves. And then finally actually collect that information for a collection of sampled packets and export that to some off-board system that's going to do the real horsepower, the real analysis of the data. So just to view that visually, you're going to filter, sample, extract information from the sample packets, and export. So you can reduce overhead here in a couple of ways. You can filter to only look at a small subset of the packets, like just the web traffic or just traffic going to a particular customer. And you can also reduce overhead by sampling, by doing 1 out of 10, 1 out of 100, 1 out of 1,000. The key point here is the router's not doing anything else with the packet except shoving those key bits about the packet into a queue and shipping them off. There's no flow cache, there's no heavyweight state, just a small queue to bundle up the records into a packet, very lightweight. Then so what you want to do is actually maybe have not just one of these instances of this filter, sample, extract, export, but maybe a small number, like 2 to 4 of them. Because actually one problem we often find in the AT&T backbone is actually multiple different groups within the company that are trying to use the measurement data. One group that might be doing basic network operations functionality that wants a coarse grain but overall view of the traffic. Another that's trying to drill down and try to diagnose a DOS attack. You know, another one that's studying a particular high-profile customer. We want to be able to support all those groups, and they each need an independent view of the data and a different way of slicing and dicing the data. So the idea would be to have multiple instances of these, but just 2 to 4 of them. You can't really have thousands of these in parallel and have it implemented at high speed. So we'd like each of these to be independently configurable, to have a different ACL in the filter, a different sampling rate, and maybe even a different sampling methodology. One might be random, another might be hash-based, feeding off the different collection systems that are used to operate the network. So earlier I said I wasn't going to put anything in the lower part of the slide, but I couldn't resist adding this one. So this is a URL for the packet sampling PSAMP working group. So I encourage all of you to check it out. It's still a fairly young group, and we're at the stage of defining exactly which bits in the packet header should be involved in the filtering and sampling filtering function and which one should be extracted, and also how the sampling unit should export data to an off-board collection system. For example, how to make it congestion friendly so you don't overload the network with measurement data. So there's a lot of opportunity here to influence how the PSAMP group goes. But the end goal is really have ubiquitous support to have effectively what we should have had all along, which was to have measurement be a first-class citizen in the design of IP equipment. On the routing side, what we'd like to be able to do is get a continuous view of the IGP topology and also the routing information from neighboring domains. So right now you can do this in 2 main ways. One is you can just go to the routers and dump their link state database or their BGP routing tables. And that's good because you see not only the current routes, but all the information that led up to the selection of those routes, the alternate routes, the entire link state database, that sort of thing. But it's extremely heavyweight, and as a result of that, you can't do it very often. It's once an hour, once a day at 2 in the morning, walk through the network, grab hundreds and hundreds of BGP tables. So it creates a large amount of data, can only be done on a coarse time scale, and it's very hard to join data from different routers because they're not collected at exactly the same instant in time, and in fact may even be spread over a period of hours if you're trying to walk through a very large network. Also, it has an overhead on the router, so you do have to be careful how often you do it and at what time of day even that it's done. On the other extreme, you could have a separate box, a software router, running Zebra, running GateD, whatever, setting up a BGP session with one or more of the operational routers in the backbone. And this has the advantage that you can get a continuous feed live and maybe even run queries on the data directly on this separate box. But you've got a problem too because you're only seeing the best route and only the best route from the particular vantage points that you've set up your monitor to connect to. You also have a problem that you only see the routes after the import processing has been done on the router you're collecting the data from, so it's very difficult to emulate what a different import policy might have done, what routes would have been filtered, what different attribute manipulations might have been done with a different routing policy. And then finally, those monitoring boxes can be very vulnerable to congestion and transient failures in the network, when you might lose your connectivity to the operational router, and that effectively causes a reset and a huge amount of new BGP update data or OSPF data when the new adjacency comes back up. So those are the disadvantages. So what we propose is a lightweight onboard support for route monitoring, where the router can set up the session with a separate box, so very similar to the second option I described on the previous slide, but it's doing continuous export of the received routing information, not the best route. It's not treating this other box as an operational router, it's treating it as a monitoring box and passing to it the extra information that we think that box needs. So it's going to send the routes before import processing. It's going to send the best and the alternate routes. And also there needs to be some ability to tolerate transient problems in reachability, so we don't have these issues of resetting, if you will, the session with the monitoring device. There's some luxury here, though. So I'm asking for extra functionality for this session, but we do have some luxuries as well. It doesn't have to obey the routing protocol format, message format, strictly. And in fact, it may actually be desirable not to, so that there's not a risk you actually hook up an operational router via one of these sessions and mistakenly send it too much routing information. It can be a more concise format that's geared towards measurement, and it could omit some redundant information, particularly in IGPs. It could omit things like hello messages and refresh LSAs that we really don't care so much about. So to conclude, basically what we want is to be able to do network control functions that require a network-wide view. A network-wide view of the topology, a network-wide view of the traffic, a network-wide view of the routing information within the network and with neighboring domains. And we think that really that benefits a lot from having lightweight support on the routers and on the interface cards. And lightweight because realistically we're not going to get ubiquitous support on high-speed interface cards unless it's lightweight. So I presented two things, the packet sampling effort, which is trying to do extremely lightweight, almost stateless sampling of the packets as they go through the interface card, and also a route monitoring session that will give a network-wide view of the best and alternate routes in the network. Thanks.
I don't want to keep you folks at lunchtime, but let's take one question if there is one right now. Does anybody have one? Okay, and we'll move along. Mujahid.
Let's try this again.
So I'm with Sprint Link Operations. So I'm going to just try to keep it short so that we can all make lunch. So the three main tasks that we have to do in dealing with the DOS attacks are, detecting the attacks, tracking them, and then finally, doing something to stop them. We had a pretty good BOF last night, and some of the folks who were there, were brought up pretty good observations were brought on, which is pretty much in line with what we are seeing. and what the customers were experiencing. We heard some of the big customers asking the vendors and also the ISPs to implement things that are missing, which they would really like to see. What Jennifer and Christoph discussed, what we are missing on the routers, which are needed, and that's good. Those are the good things to have on the router line cards. So we won't have to put any of the external devices to do the monitoring that is for collection of the data that's needed to detect these attacks. So right now we have limited tools available to proactively monitor and report DOS attacks. Some of the customers do expect it, but there's a price attached to it because right now the tools are not available on the routers. So we have to use some of the external devices to get the data out to those devices and then analyze the data to detect, proactively detect the attacks. So that's the key thing today. It's got a price tag attached to it. And there are different approaches to how we can detect, and some of them are, like you can see up there, inline detection, flow-based, which is mostly using net flow type stats off the routers and then sending them out to some data collector and analyzing. We might have some passive tapping detectors, something like what Christoph talked about, that we put in the network to look at the packet headers and then evaluate and analyze that data to detect attacks, or some form of IDS in the network to get that data and do the analysis. To have all of these would be great, but again, the key is it would have to be widely deployed. Plus, there's a price tag associated with it. So I'm not sure if it's being done on a wide scale in a tier 1 ISP network. So mostly the proactive detection is the customers calling their ISPs and saying that they saw a sudden increase of jump in the bandwidth utilization or the resources on the routers going is just peaking. So that's the proactive monitoring that's happening right now. So the need is to detect the attacks fast, figure out whether they are legitimate attacks or it's just the normal traffic because someone put an application up there on their web page and people start downloading it. So you have to have smart tools to detect that. So this is basically summarize what I said. Like I said, the tools that we should have to be scalable. They have to be distributed, where they can get data from different points in the network. And the key thing is that they should have to integrate with what we have in the network today, all the routers and all the infrastructure that we have. The issues with using inline or IDSs is that they would have to be put in, to be distributed and be useful, they have to be put in many places in the network. So that would add to the cost. Plus that in case of inline way of doing this, that might add a point of failure in the network. Again, the flow-based it might not be available on some of the platforms in the routers, plus the storage and computation requirements may be expensive again. Then we have to, once we detect attacks, we have to track them back as to where they're coming so that we can do something to stop them. Again, this today is being done differently by different people. We discussed some of the methods at the last BOP that a few of the ISPs are doing. Barry's with Cisco is doing pretty good work at that in trying to let people know as to what they can do with the deployed infrastructure out there today. So the issues in detecting that we experience is the randomness in the attacks, the source addresses are spoofed, and it's just the fan out. If the fan out is big, it makes it pretty difficult to track them. So whatever tracking schemes that we might have to deploy, it has to be fast, and it has to be deployed network-wide, so that it covers almost all of your ingress points, which kind of becomes an issue if there are a lot of sources which are spread out over the network. In some of the methods, so what Sprint we are using, some of the methods where we're using backscatter, in some cases we have to null route the victim's IP address, or reroute the victim's IP address to analyze the traffic that's headed to the victim to figure out where the traffic is coming from, what kind of attack is being launched at the victim. So, which might not be desirable in all cases where you have to take a valid target and sort of null route it or reroute it. So that might not be a desirable thing to do. So most of even though we have ways to deploy, we have found ways to deploy some of these schemes faster. Still, a lot of this is manual, and so it's kind of slow. So by the time you get to locate your sources and do some damage control, it might already be too late. So now, once we track the attacks, what do we do to stop them? So right now, mostly what everyone else is doing, or everyone is doing, is putting filters once they track the attacks to some of the sources, and it's usually done away from the sources. It's to be effective, you do it like away from the source and at the ingress of your network. Or you rate limit the attack if you know what kind of attack is being launched. One of the same point I mentioned earlier, that sometimes you end up blackholing the target's IP address, which might not always be a desirable thing to do. Other observations are that unicast RPF has helped, and I think we had a pretty good discussion about this last night in the BOF. It has helped, and we are using it where it's applicable. Where in some cases we are doing strict URPF, and in some cases where we can't do strict, we're doing loose. Again, what we do to fix the problem is deploy filters, which is basically not taking care of the root cause. We're just putting band-aids. So the root cause is there, which is which people might be finding ways to get around those filters. Again, so some of the observations, the solutions, whatever we come up with, have to monitor, detect, and analyze DOS attacks, have to be distributed. They have to be widely deployed across your network. It needs to work with whatever router base you're using, whatever the deployed infrastructure is. It needs to be compatible with that. Again, going back to the points that Christoph made and Jennifer made, is that we need features on the line cards. That's the best thing that we can get. But again, it's not available today, and if some of the features that we have today, turning them on impacts the performance. And if some of the other schemes, if we use to detect these attacks, if they are external to the routers, they have to have minimal impact on the deployed infrastructure. And we have to just keep that in mind, that in some cases we might be adding a point of failure. Last, which is getting pretty good lately, is coordination among ISPs. We have a mailing list going for security, and that's helping a lot in tracking and somehow mitigating these attacks faster. It's just some of the initiatives that we have at Sprint. This is near-term and far long-term work that we are looking into. So we are looking at, different vendors, what they're doing and what's available out there, which might be applicable on our network. We are also looking at ways to detect the attacks using the packet header trace that Christoph's group is working on, and some of the other techniques to sort of integrate that data with some of the routing data available, for example, BGP routing and IDS logs, and etc. That's about it.
So according to my calculation here, we're still behind. I want to give Chris a chance to talk because he's been so patient up here, and then we'll go for questions or lunch, whichever comes first. I'll try to be fast.
Okay. I'm Christian Martin. I work for Verizon. And ironically enough, it looks like some of the concerns that were raised by some of the other panelists are the topic of my presentation, and that's not intentional. I'd like to say it was, but we didn't coordinate beforehand. As you can see, the title is Coarse-Grained Traffic Analysis in ISP Networks. It's a router-based approach. And I'll start basically by discussing the traditional methods that we've used and then go through what I think we need to be doing in a modern analysis paradigm. So traditionally we looked at things like resource utilization, CPU port memory. We've characterized our traffic based on flow information through NetFlow-based tools, source, destination port, protocols, things like that. To try to determine what kind of traffic is flowing across the network and in what magnitudes. How do the application phenomena affect traffic dynamics, things like Napster and EverQuest, I think everyone remembers that a couple of years back, and Kazaa, things like that. And of course we're looking at network performance, round-trip time, packet loss, maybe using it to offer up some SLAs, and also to kind of see if there's any problem areas in the network that we should be addressing. I think today what we should be looking at is some more detailed analysis, and it's becoming more and more evident, especially seeing the presentations that we've just witnessed, that there's a lot of analysis going on to try to determine really what's happening on the network, not just link scope or maybe CPU utilization or things like that, but really what the end-to-end look and feel of the network is. So I think one of the first things that is really important is node-to-node coarse-grained volumetric statistics. So nodes could be ASs, they could be routers, they could be POPs. And those are important. This data is important for traffic engineering, for metric assignment, and for billing, and maybe numerous other applications. Another important thing that I think that some of the more regional ISPs are looking at is ISP to ISP, and then ISP to maybe a set of ISP traffic lines. I call it peer seeking. I don't know if that's a word. Vern, maybe you can tell me if that's acceptable. But I think it helps. And I think a lot of ISPs are looking at seeing what kind of traffic they're exchanging with other ISPs to determine if there's appearing synergy there. And of course, traffic characterization, a lot of it has to do today with doing topological and routing data correlation, which is kind of difficult. You have to export a significant amount of data. Christoph was saying that they were collecting a terabyte of data a day. So you need some significant infrastructure to do that kind of analysis, and then a lot of processing power, a lot of disk space, and that's expensive. And then I think another area of concern is temporal analysis for network performance, jitter and convergence times, and any kind of real-time analysis. Security threats are occurring in such a rapid fashion, and we're so slow in responding to them that they're gone before we know what happened. And this analysis is hard. A lot of research going on, 4 or 5 years. People have been doing this work, and we're still moving forward and maybe taking baby steps, but we're getting somewhere. So I think the best way to define the difference between the traditional analysis and the modern analysis that we should be doing is by using a term from literature and defining the way a term or something means. Either there's a denotative or a literal meaning, and that's kind of like just what it is. It gives sort of a dictionary definition of what's happening. So if you look at a link and determine that you're moving X bits per second, that doesn't really tell you much about what's on the link. It just tells you that the link is doing something. And in order in-person meaning, we need a heuristic, something that gives us a rule of thumb or a pointer in the right direction. And the one such heuristic that we use most is the routing table. So modern analysis, connotative, we want to get implied or inferred meaning from what it is that is happening in our network. And some of those things may be like traffic between pop A and pop B, or maybe a relative increase in a certain traffic type between 2 different ASs. So the routing data itself is a heuristic, and our modern analysis requires an understanding of the routing state of the network in real time. Otherwise, any empirical data we have is meaningless. So gathering that information offline and then correlating it is somewhat of a difficult task. In military networks and in military simulations and things like that, they use I guess I don't know if you'd call it an area of specialty, but it's called centrifusion, and that is essentially dealing with massive amounts of data in real time and trying to be able to analyze it and present something to maybe an operator. It could be a fighter pilot, or it could be something like that. And it's similar in that we have all this data that's coming from all over the network, and we're trying to do something with it, and it takes an enormous amount of time to analyze data at the magnitudes that we're looking at. It's costly to do offline calculations, as was suggested by other panelists, because you have to deploy all this infrastructure. And it's disruptive, so you're inserting probes maybe on your links. You have to go through maintenance windows to insert servers into the POP so you can pick up the analysis traffic. And it's inaccurate in the temporal dimension, because when you're grabbing tables, for example, off a router, you take a snapshot of the routing table at that instant, and by the time you get it and do something with it, your flow data has changed. So what you were analyzing before may not be correlated to what's happening in your network in terms of routing state. But above all this, the router has the information in and of itself. It has real-time routing data and also has real-time flow data. So maybe the router can provide some traffic analysis for us. So we're talking about a router as a traffic analyzer, and I'm not talking about a sniffer, but just using the router, extending some of its capabilities already to give us some traffic analysis. And of course, legacy software routers were smart, but they were kind of slow. And then with the surge of internet traffic, so we went to a hardware-based solution that was kind of dumb and didn't have much features. And that's kind of where we are right now. We're in the process where there's some legacy software routers out there, there's some original ASIC-based routers, and now some of us have some newer routers that have, or newer hardware that has some intelligence in the ASICs or in the parallel processing engines. So if the forwarding engines are derived from routing data, and the routing data is generally distilled a great deal before it's programmed into the FIB, perhaps we can program the FIB with a little bit of additional information that we can use as a hook into traffic passing through it, sort of like a turnstile at a subway. Maybe you can put an association with that turnstile, so every time a packet goes through, that increments something like a counter. So what we would do is store things like who, which may be the next hop, or route. It could be whether it's a POP route, for example, or a peer route or a customer route, when it was applied, where it came from, things like that, and then associate buckets with those characteristics. So that when packets went through, you would match like a flag maybe in hardware and increment a counter. And then those counters, and it could be packet counters or it could be bytes or a combination, they're stored in memory and they cycle through. So you have maybe a 64-bit counter space, and once you get to 64 bits, you wrap around. And as long as you're pulling that data out of memory and storing it somewhere, you don't have to worry about storing massive amounts of data and exporting it. So applicability-wise, of course, we're talking about coarse-grained node-to-node analysis, and one of the easiest things, and I think something that everybody's interested in, is getting demand matrices. Traditionally, that is something that required a lot of offline analysis. You had to correlate routing table data with flow statistics. You have transient links or transitive links that are carrying traffic between two POPs, and you have to get their data as well. So this gives you a way to get that kind of information really simply. You can also do the peer-seeking application, which is similar to what you would do today with net flow analysis, except it's routing data in real time. And potentially down the road, we can get some fine-grained analysis. Because we have real-time data on the routers, we can potentially, with the right hardware additions, maybe do some data pattern analysis using router-based heuristics, and then do some inferencing and maybe reacting. So for things like DOS attacks, you can maybe analyze patterns or changing patterns in your data with microburst analysis. You don't have to wait for 5 minutes for some smooth that average to really, maybe over 10 or 15 minutes after that data starts to accumulate for you to recognize a problem. And anything that requires routing information for correlation, and then maybe down the road, not only just routing data, but maybe we can do things with flow data and routing data combined. So maybe you can get NMTP statistics between a set of ASs in real time. And this is not sampled. This is one-for-one packet counting, but it's not something that's done in great detail. You have to have knowledge going in. So as an example, we can look at here on this fine-looking network drawing that we have a couple of routers, or they could be nodes, it could be ASs. And what we're saying here is that any two end nodes where the larger arcs or the larger double-sided arrows, we can use information based on the routing table and these flags that we're setting to determine the traffic that's going between them. And it's just aggregate. It's nothing interesting about the traffic, just volume. Peer-seeking again, if there's an OS over here on the left, and two transit providers, and then there's a potential peer who may have some customer ASs behind them. And traditionally, NetFlow will show you, for example, origin AS. So you have to go about the task of correlating that data and identifying the fact that these origin ASs sit behind this particular AS before you can really determine how much you may be sending to this potential peer. And then I might note that NetFlow processing, even today on today's routers, is expensive for AS information because the AS information is in the BGP web. So you can't do anything about that in hardware regardless, unless we start programming the BGP web into hardware as well. So again, fine-grained analysis, there's potential for interesting work here with additional hardware. It doesn't have to be in line cards. I think, depending on your vendor, you could probably copy packets from one ingress line guard to an analysis line card on the router and still have high-speed correlation of routing data without having to export it and do the analysis there. And what we'd say is by offloading analysis to the hardware and the router, we ensure temporal accuracy because it's right there. And the data is transient, and it appears to be self-similar. Again, I was with Tony last night, and we were talking about whether or not traffic was self-similar. But if you look at most graphs, at least on a macroscopic scale, it does appear to be self-similar. So it'd be hard to argue that traffic dynamics change that much from day to day. So you probably can dump the data you had the day before if you're only looking for coarse-grained information. So there's some caveats. BGP is asymmetric in terms of what you're sending versus what I'm receiving, particularly in AS. And that may be something that you'll have to do something about. But within an AS, I think we're pretty symmetric. And you have to have, there's no a priori approach to rule setting, so you have to have an idea of what you're doing beforehand, so maybe some NetFlow stats or something like that. And it does require a hardware and software upgrade. So ask your vendors when and where this capability is supported. So the routers have the data today. The parallel processing engines and ASICs are advancing along with traffic volume on most networks. And as we know, inline probes and offline analysis and things like that are expensive. And this is not a replacement for anything. It's complementary to what we have, SNMP2 or MIB2 and if MIB stuff and flow statistics. Thanks.
Well, okay. Do we want to do questions, or do we want to have lunch, or both? Questions, anyone? Comments, anyone? Go ahead.
Hello? Thanks. Hello? I was wondering, so people have talked about, various different approaches to handling what seem to be kind of coalescing into a common set of tasks or goals. you know, and then we've got the vendors who are trying to accommodate us. Do people think that, you know, the BCP should be written on what, you know, what people are interested in looking at, and then some sort of unified set of requirements delivered to vendors, so it's not just people popping up here and there, oh, I think I want this, well, I think I want that, and, you know, them having to sort out the, you know, what to do with all the, you know, with the limitations they have on ASIC development time, space, and, you know, all the other things.
I'll take a stab at that on the traffic side. That's effectively what we're trying to do with the PSAMP working group, and there's a lot of vendor involvement there as well. And the primary goal was to pick functionality that really can be implemented in the line cards, so that it's socialized with the vendors before we make outrageous requests on what they try to put in the line cards. On the routing side and on things like active measurement, I don't think that's been done as much, but one could imagine doing that.
Go ahead.
So on that topic, when we go to routing vendors, if we're going to put together a BCP for routing vendors, I think it is very much necessary for us to come up with a, as you say, unified set of requirements, because when I go to a router vendor today and say, hey, your SNMP count is even something very basic, don't work on X, Y, and Z, they say, oh, yes, but that's down here on our priority list because I've got these other customers that have much higher priority requests. I think if we were able to say, you know what, here's the collected set of large ISPs, we all want the same things, we're all going to come to you individually, otherwise you're not going to get nickeled and dimed by one person or the other. Here's what we all want, here's what we all need, we're going to have a lot more leverage. I know for one, I've been very frustrated in trying to go one-off and say, why is it so hard to get good stats from you guys as vendors?
Go ahead.
Yeah, on the BCP, inside the IETF, IPPM, so that's the Active Measurements Working Group, there is a first attempt towards the BCP, though at the moment it's more a list of topics to be addressed than any content. And I'm editing it, and I would welcome any contributions.
Thank you. Anyone else? Don't forget to fill out your, what is it, the blue, isn't that the blue sheet? No, that's with the IETF, sorry. Survey, yeah. All right, thank you, everyone.